Okay, so I'm going to do a series of videos to go through all of the alcohols pack, and you can have a look at those. So just starting off with the alcohols then. So the alcohols have the functional group of the OH. Because of the OH, it has a polar bond in it, which means it's going to be more reactive than the alkanes because it can attract electrophiles or nucleophiles, which we'll talk about a little bit later on. Because of the OH, they can form hydrogen bonds with themselves, which means they're going to have quite strong intermolecular forces for small molecules, which means their melting and boiling points are going to be higher than their corresponding alkanes. Alcohols are all liquids because of hydrogen bonding. In terms of solubility, again, they have a tendency to be soluble because, again, they can hydrogen bond with water. However, as the alkyl group here gets larger, the amount of hydrogen bonds that can form gets less and less and less, which means they become insoluble as the chain gets longer. In terms of the namings of them, so they end in ol, and we don't need numbers if they can only go in one position, but we use numbers if obviously they can go in any position here. Classification, we did touch on this before we kind of finish, and this is absolutely crucial in terms of the reactions, which we're going to deal with a little bit later on. The thing we need to be able to do is classify them as primary, secondary or tertiary. So what we do is we look at the OH group, we put a star on the carbon that is attached to, and then we count how many carbons that starred carbon is attached to. In this case here, it is 1, which makes it a primary alcohol. The only exception to that is methanol, and of course if it's got no carbons attached to it, that will also be primary. With secondary, we do the same. So there's the OH group, there's the starred carbon, and then you count how many carbons that's attached to, or how many alkyl groups, and we've got 2, which makes that secondary. And then with the tertiary, there's the OH group, there's the starred carbon, and it has 1, 2, 3 alkyl groups attached to it. So that's how we classify them as primary, secondary and tertiary, and it is absolutely crucial that you can do this for the reactions that occur a little bit later on. So there's 2 ways that we can make ethanol. We can either make it by fermentation, which uses sugars, and it undergoes anaerobic respiration or anaerobic conditions. That's without oxygen, and we use an enzyme in yeast. And because it's an enzyme, you can only really work up to about 40 degrees centigrade. Problem with this is you only get about 15% because the alcohol kills the yeast, which means the reaction effectively stops. It requires a secondary process after that, which is fractional distillation, in order to separate the pure ethanol from the watery mixture that's left behind. The second way we can do it is by the hydration of ethene. The conditions for this is 300 degrees C, phosphoric acid catalyst, 60 atmospheres. And because it's at 300 degrees C, the water is going to be as steam. So the mechanism for this we did in the alkenes, and it's worth having a look over those again. Just to make sure that we're aware of where this hydrogen ion comes from. If we have phosphoric acid, it will dissociate into 3 H pluses plus PO4 3 minus, and it's this that is this. So it's positive, it's got space in its electron shell to accept a pair of electrons. The carbon-carbon double bond is electron rich, which means these 2 attract each other. So this is an electrophile then, this hydrogen here, and it accepts a pair of electrons from the carbon-carbon double bond, which goes on one of those carbons, and I've put it here. That gives you a carbocation. Water's next. Remember, water is polar. It has a D plus end and has a D plus end and a D minus end, and the D minus end there is going to be attracted to the positive carbon. The pair of electrons on the oxygen will form a dative covalent bond. And now remember, in a bond, normally one electron is provided from each atom, but oxygen here is providing the electron it normally would plus an extra one, which makes that oxygen positive there. So from there, the oxygen-hydrogen bond has to break, so the pair of electrons in that bond go back on the oxygen, which puts it all back together, basically. So have a look over that in the alkenes. It is important because when you've got unsymmetrical alkenes, you can have two different alcohols formed. In terms of the two processes, comparing them, fermentation tends to be from a renewable source and is deemed to be carbon neutral, which we'll deal with a little bit later. It's not pure, you only get about 15%, which means you need to do distillation after that. You can't speed it up really because at temperatures over 40 degrees C, the enzyme becomes denatured. And it's what we call a batch process. So you make a load, clear the apparatus out, start again, make another load, and so on. The setup costs are pretty low, but the labour costs involved are quite high. So it's an expensive ongoing cost. The other type, hydration, this comes from crude oil, which means it's not renewable. And of course, therefore, it won't be carbon neutral either. The product is pure because you only get one product, and we can manipulate the rate of the reaction so we can make it quickly. It's done as a continuous process, so there's no need to stop it. However, the setup costs are pretty high, but once it's set up, the labour costs are pretty low. So as a fuel, it's pretty good. The sugars are the sugar is a renewable source, whereas it's also a carbon neutral process. However, when you're growing the crop to make the sugar to do the fermentation, you have to be careful that you're not using space that was used to make food. There's deforestation, loss of habitats, and so on and so on. But let's have a look at why the fermentation process is deemed to be carbon neutral. During photosynthesis then, 6 carbon dioxides here are taken from the atmosphere to make 1 lot of sugar. That 1 lot of sugar, when it undergoes the fermentation process, makes 2 lots of ethanol and 2 lots of carbon dioxide. These 2 lots of ethanol, when they undergo combustion in a car engine or something like that, it releases a further 4 carbon dioxides, making a total of 6. So it looks on the surface as if it's going to be carbon neutral. But the thing you've got to remember is that we need heat for fermentation, we need heat for distillation, we need the transport costs. So on the face of it, it looks carbon neutral, but in fact, it wouldn't be. So that's that. So we'll leave it there for that one, and we'll look at the next section in the next video.